Okay, hey guys, here are numbers and names number 8. Today we'll talk about axioms and paradoxes, but before I want to ask you, how about previous questions? And also, do you have questions for the previous lectures too? Maybe something appeared in the air? How was the questions? Did you answer them? Did you discuss them at least?
We did not get a chance to discuss them. We discussed them right afterwards, right after the lecture. We usually discuss them.
Okay. So, did you?
We did.
And any results?
Well, you asked us to come up with paradoxes or with theorems, right? I think we had a couple of ideas. I don't remember them off the top of my head.
Okay, how about this infinites and zeros? Remember infinite squared?
Oh, those things. But we discussed it, and well, from the point of view of algebra, I didn't even know how to follow on that. I mean, you can't divide by zero.
That you are talking. What about kids?
What is 0 divided by 0?
That's undefined.
Eh?
It's undefined.
Undefined?
The children are biased.
No, of course there is a rule, right? There is a rule which you memorize, right? 0 divided by 0 is undefined, blah blah blah, right? But 0 is still 0, infinite is still infinite, right? So if you think about it in from other point of view, okay, you can, like, for example, can you add 3 and 3?
Yeah.
Okay, it will be 2 trees, right? Can you add? Yeah, wait. Can you add 2 galaxies?
Yeah.
Can. Galaxy plus galaxy. Can you add universe plus universe?
Yes. Did that.
Okay.
Did that. All of this, if they're like x plus x, only the same things with the variables can add together.
Yeah, actually, infinite is still something, and you can add it. Why not? If you think that infinite is the same, right, or any infinite that you take is the same, you can add them, you can subtract them, whatever.
But it's not the same. Like that's the point. Like a number 5 is the same, but infinity is not the same.
Okay, why infinity is not the same? Okay, just give me any other example in the universe that you cannot add or subtract.
Like, isn't a universe plus a universe still a universe?
Yeah.
What do you think?
Yeah.
Can it be 2 universes?
Is it even bigger? I don't even know if it's bigger.
What if they crash? Something bad could happen and it's half the size.
Okay, I can ask you another thing. 1 and 1. 1 and 1. Are they the same?
Yeah.
Exactly the same. Why adding 1 to 1 can be something else than 1? It's just the same thing. You just take it 2 times.
One is 2.
So what is 2 then?
Well,
A number?
no, with 1 you have a 1 and you can consume it and you can use it and you can see it. But with infinities you cannot do either of those things.
You can think about it. You can operate mathematics whatever you see or you don't see. If you can operate only those things that you can see, there would be no mathematics. There would be something else. That would be practice, right? I take one stone and another stone, bam, and what is it? It's not mathematics. It's 2 stones. Actually, I cannot even use 2 because 2 is from mathematics. So stones. What I mean that it's a little,
But if you have like for example, if you subtract a countable infinity from uncountable infinity, like it's still an infinity.
But with infinity.
It's the same, uncountable.
No, okay. You are talking about 2 infinities, or if you want to subtract one infinity from another infinity, right? You still have infinity and infinity. The one infinity and the other infinity. We are talking about 2 infinities or not?
Yes.
When we want to subtract, even we put subtraction, we have one and another one. And they are the same like 1 and 1, they're exactly the same. So 1 minus 1 is 0. What would be this? Eh? Okay. The reason why I ask all this, because it's, of course, that's definitely, it is a very useful thing. It is used in, not in algebra, but in calculus, right? And in another way, in a certain way with, like Antosha, your papa said, limits and whatever. But even without limits, actually, there is a way to talk on these things without coming to limits at all. It's called non-standard analysis, non-standard calculus, probably in English. So, and they have this infinites and zeros like certain things. They talk on them like some certain entities, right? Like universe or whatever. But if we have one universe and another universe, and the universes are the same, and you just remove this, what is subtraction? Just removal, right?
Yeah.
So this is one universe, and the universe is infinite. So one universe, and we actually removed it by using this operator, this operation. So we removed it, and then there will be no universe, right? So there's still logic there and logic here. So just be careful with these things. What I want to understand, that mathematics is not as simple as maybe you think. They sometimes, when the teachers are trying to explain, they make it simple, but it's not that simple. It's very, very paradoxical and very mysterious in many ways. If you go deeper in practically any place of mathematics, you will find a lot of questions. Unfortunately, teachers try to, to remove all these questions, just say, looks like everything is okay. Did I tell that in the beginning of 20th century, there were two guys, pretty smart mathematicians. Unfortunately, I forgot their names, right? And they were writing the volume on mathematical logic. Did I tell this story? Yeah?
You told this to me.
Okay.
Apartment, remember?
Okay, so I just repeated, just for example. It was right beginning of the 20th century, right? And they wrote the first volume and they published it. And the logic, mathematical logic, was so complex there that there were not even one word, maybe some few words. All the rest was formulas. So the whole volume was just full of logical formulas, all this volume. Then they wrote their second volume and wanted to publish it, and then suddenly was discovered a paradox in deep roots of mathematics. It is in common speak. It's called a Barber paradox. I think I told you this paradox, right? Barber.
It doesn't sound familiar.
Barber is a guy who is shaving other guys, right? Like who's shaving, like for example, shaving the beard, right?
Yeah.
So the question was, in one town there lived a barber who shaved beards from everybody, but only those who do not shave themselves.
That's weird.
No, that's okay. They do not shave themselves. They call the barber. That's normal, right? So he served them. He shaved their beards, right? The question is, so that was the only those guys. The question is, does he shave himself?
Oh.
If he does not, he should shave. But if he shave, he should not. Okay? So there's a paradox. It's called Barber paradox. And it is pretty famous because it can be formulated in the terms of mathematical sets.
Russell's formula.
Sets. You know set, right?
Dida.
Oh.
Dida.
Oh.
Aren't you going to use Russell's theorem?
No, I don't. I'm not going to talk on this at all. Just an example, okay? So just be careful with this, and now we go further. The first I wanted to ask you and your papa, actually. Just by the way, can you see what I'm drawing on the board? Or
Yeah.
We can, because I have my pen is a little. I think it's a little old. I need to buy another pen. I need really, guys, really to discuss, because the thing I'm telling, they are very complicated. So better to discuss them, you know, to play with them a little. It will be funny for you, and you will be easier to understand the next things. And please do so, okay? And Antosha, Papa, please do so too, okay? Now, let's talk about like axioms. Axioms are actually laws, right? Laws of whatever theory we have. And law is, what is axiom? Axiom is some true statement, right? So some phrase that is always true. Always true. And never false. Something like that straight parallel lines would never cross to each other, right? Like for example. And if we look around, we will see really parallel lines that are actually crossing in the space, right? But still, remember I told you about a pretty famous guy, mathematician, Carl Gauss, who invented and never told anybody non-Euclidean geometry. So he was so doubtful that he actually climbed with his assistant. He climbed to the three mountains around him, and he triangulated with the special devices, right? He measured the angles in the triangle between the summits, the tops of these mountains, the angles. He measured these angles. It's a huge distance, right? A few miles or something like this, three mountains.
They made an isosceles triangle.
Yeah, he wanted to find out, is our geometry is really Euclidean? So do these three angles, some of them, would it give 180 degrees? Would it give 180 degrees? He got 180 degrees, or near this, right? So he cannot find actually, is it? It looks like Euclidean. But he had doubts, really doubts on that. And anyway, he had doubts, but he never published his work. And it was published by other people who actually are official discoverers of non-Euclidean geometry.
So was it 180 degrees because the mountains just were not far enough from each other?
In reality, yes. If you really measure degrees not between the mountains, but like between the planets, right, in our solar system, if you can, it was never done because we still don't have such a measurement devices. But if we do it, yes, the number of degrees will be different.
Where I'm sorry, say it again.
Between the planets, like our sun, right?
Yeah.
And some planets, or maybe three positions of Earth, right, in different times.
Yeah.
If we can measure this triangle, the sum will be different.
Why?
Because we live in non-Euclidean geometry. Our geometry is not Euclidean.
Dada, so if we live in non-Euclidean geometry, then how is there Euclidean geometry?
Yeah, that's a good question, right?
It works on the small scale, I suppose.
Yes, in the smaller scales it looks like Euclidean. Yes, it looks like. And it's difficult actually to distinguish the difference, but it's still there. There are other, thanks God, there are other ways to find out is our geometry Euclidean or not, and it was done actually. There was a famous experiments which actually were successful, and the curvature of space, it makes our geometry of our space non-Euclidean. The curvature was actually measured.
But I have a question for you.
Sure.
If we just take a triangle on the surface of a tiny ball, wouldn't that not add up to 180 degrees?
But we spoke on this, right? So if you talk about like 2D, two-dimensional geometry, right?
Yeah.
2D geometry on a ball, right? On the surface of the ball, it is not Euclidean, yes.
Yeah, it would not add up to 180?
No,
Would not.
would not. Remember, it could be anything. By the way, remember, we were drawing these triangles, right? Like this triangle, it's one angle, and another triangle, you know, would be that angle, and another triangle, that angle. So it would be any numbers of 180, not 180, more than 180, less than 180.
Did I have a question?
Yeah.
The Euclid guy, how did he come up with the idea that triangles should be 180 degrees?
Well, that's easy to prove.
This is proved in Euclidean geometry.
Yeah.
They have axioms. Remember the axioms, the laws.
That's not one of the axioms, though. That can
No,
be
it's not axiom. It's a theorem. It's proved.
You did experiments with triangles.
By the
I'll show you the proof.
yeah, okay. It's interesting. Yes, you can get it. By the way, you should understand one thing, that you take like laws of geometry, right? They are axioms of geometry. But there are not only these laws that are used when you prove some theorem. When you prove a theorem, you use logic, right? You say, if this, then this, if this, then this, and go step by step by step. And then they come to a proof. When you're proving certain things, you're using not only axioms of geometry, but also axioms of logic. So there are two sets of axioms. And they all should be true, right? All axioms, this law should be true. If not, because that not only our geometry of our space is actually non-Euclidean, we know that, but actually our logic could be not that good logic as we use in like our regular talks and mathematical proofs. There are lots of other logic with the different axioms actually. So just quite opposite to the axioms that we use regularly, like when we talk and when we prove our theorems in mathematics. So mathematicians know that, but it's they live with it. They find a way to live there. But what they don't find a way to live with it, those are paradoxes. And actually, unfortunately, paradoxes are everywhere too. And then we talk about these paradoxes a little more, just to get the mystery of mathematics. Okay, so let's talk about a simple thing. We have darkness, and we have light. Two things opposite to each other, right?
Yeah. Wait, what's that light?
You cannot see in the darkness, right?
Well,
Yes, question?
well, Dita,
Uh-huh.
sort of can, really depending if there's any objects that will bounce off the light. There's two different rooms.
Well, if it's dark, there's no light.
Oh, yeah.
Yeah, darkness, no light. Actually, they negate each other as we speak, as we say, right? Darkness is not light, no light, right? Light is no darkness. So they are opposite. Okay?
Yep.
Okay, but interesting thing, we cannot see in the darkness. Can we see in the light?
Yeah.
Are you sure?
Yeah.
Like, for example, imagine that there's all light everywhere. Everything is light.
Would you get blind?
And no shadows. Shadow is a darkness, right?
That would be too much light. Oh, wait, if there's no shadows, that means there's no light.
No, there is light. Everywhere is all light. Light, 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 and not even one small shadow. Do you see anything?
No, I doubt it. No, you wouldn't be able to. You can't. Because
It's-
you can only see white.
It's like a fog, right? Like imagine a fog that is light out, like fog. Everywhere is light, but nothing can you see, right? That's like light. The same thing in darkness, right? So the other thing, if you want to see in the light, you should add some darkness here. So you should have some shadows.
That's interesting. In order to be able to see, you need darkness.
Yeah. The other thing is, if you want to see in the darkness, you should have some light, right?
Yeah, makes sense.
So if they mixed a little, you can see. If they not mixed, so they're absolute, like absolute darkness, don't see anything. Absolute light, don't see anything. So, and when you don't see, Is it like when you don't see in light? Is it become very similar to the darkness? You cannot see anywhere here or there. They are very similar in this way.
For example, captures light easily.
Mm-hmm. The other thing is like if you think about darkness and light, can you really transform? How you transform in reality? How you transform darkness to light? Can you do it?
You
Like,
put more reflective objects in there to see.
If there's no light, there's nothing to reflect.
You bring a flashlight.
no, it's a very simple question. It's a very simple question. Okay, everybody knows that black and white are opposite, right? They're not like. But if we have darkness, which is very similar to black, and light, which is very similar to white, so can we just do something that suddenly darkness become light?
Well, I don't know. We can make darkness non-darkness.
A candle?
No, it's very right. It's a very easy. It's a very simple question. Of course, we just turn on some candle or whatever, right? Find a candle or just turn on light, as we say, right? So there is a certain transformations in our world, which can transform darkness to light, and when you turn it off, it's go back, right? So to go back and forth. So this means actually that if you remember our talks about symmetries and everything, that something is similar in the border. How do we call the border between darkness and light, by the way?
A wall.
Huh?
A connector.
Connector. Yes, right. What connects darkness and light? When darkness becomes light or light becomes darkness, this region, how we call this situation? What's the name for this?
Twilight?
Twilight. Exactly. Twilight. And if you think really, right, we actually live in twilight. Some twilight is a little more light here, and some twilight is a little more darkness here, because usually we still can see something when we really want in the greatest darkness that we can find. The same thing in light. We can see things, right? So let's go back and forth. So it's so I think there are not too many questions on this, right? It's understandable, pretty understandable things, right? But it's become a little less understandable, but still not that big problem if you think a little. Remember this true statement, axioms, right? So we have these things which are always true, and they're here. And those is, we may tell that those is the origin of axioms. They're always true. True statements, always true. And on the other side, we can negate this, deny it totally. What? Yeah, this is the region.
False.
Everything is false there, right? Everything false. So this is absolute false. This is absolute true.
False.
Eh? Yeah. So does it resemble something? This picture to you?
A pill.
Huh? No. Does it resemble the previous picture?
This is darkness and light.
Yeah. Look at this, right? Okay, false, true. Both are opposite, right? So, okay, if here is everything false, what about false? Is false false too?
Yes.
And then it is?
That's what Visa said.
Can I tell you what? In the false place, it's a paradox.
So if it's absolute false, right, it becomes a paradox. False falsify itself and become true. The same thing is for true, because true is not false, right? And if false become true, so not true become false too. So they play the same thing like light. If we say that true is light, right, and false is dark, it's the same thing.
False in this world, otherwise it will be boring.
And we live where? In what region?
Boring, then. Because everything is correct. There's no mistakes.
In what region we live, actually?
What does that say? Twilight.
In between true and false.
Mm-hmm.
Twilight.
There would be no true if there are not some false somewhere, like a shadow, you know, which actually shows us that this is actually true, right, and not false. The same thing for false. False can be false when you have some truth that you can compare, you know, something like this. And remember this paradox of liar paradox? Liar paradox? Remember this? The liars say, I lie.
I lied.
Как там light пишется?
I lied to you, Papa.
L-I-E.
I lie. Okay, liar says, I lie. So, does he actually lie or not? If you say I lie, he don't lie. If he don't lie, he lie, right? So, it's a paradox, right? So, what is lie then? This paradox. Actually, it is the statement that actually transform true into false and false into true, back and forth.
Yup.
And how it works? If you look around, right? If you look around, that we live in twilight of true and false. There is no absolute truths, no absolute false. Some things, you know, like for example, you could say, is it day out there? Right now. Look at the window. Huh? No, it's false, right? But I would say, okay, wait for like 12 hours, right? Would be almost day. So what it says say to us? It says to us that it depends. The statement that I say, it is day now, is it true or false? It depends upon in what circumstances we actually ask this question. This is called context. In what context, right?
Yeah,
so it may be,
yeah. New York wants to be like day right now or something, or in Australia right now would be day. Exactly.
The same thing about everything. It is true about everything, and it's if you think really, it's true about axioms too. Axioms are okay because they work in our part of the universe, right? They work okay, and like Euclidean geometry, it works good in our small when we have small distances. When you have big distances like this of our solar system or bigger, okay, the geometry becomes already not that good. The same thing is for true and false, or what we say, where we use true and false, we use it in logic. And logic is talking about what is true, what is false, how we go from axioms to theorems, we prove theorems using logic, right? And go further and further and further and further. And if you look at this and you think about paradoxes which were discovered, and one of the guys almost committed suicide. He wanted to burn his second volume of this logic and killed himself. The friends, you know, stopped him from doing this, but still there was a biggest disappointment because they believed all their lives that mathematics is something like ideal building, you know, like shining building in the ocean of false, right? It's just building of truth. And suddenly they find paradoxes. And not only one, there are a number of paradoxes already formulated, like there are hundreds. So.
Question.
Yeah, question.
Isn't there an infinite amount of paradoxes?
Actually, one of the questions you may write it, right? It says, give me examples of paradoxes of your own. How many you can do? Just invent, right? But we can answer on this at least. Just write it somewhere, right? Just give this. Find the paradoxes. And the answer for this, yes. The interesting thing is that actually in each and every place we can find a paradox, because when you go, like for example, you have something, like here. Something happens here, like some event, right? And then some time passed, or you just moved to to other place, and the situation around changed drastically. Would this event could not happen here? In many cases, it happened here, but could not happen here. So you may talk about this event is true, it happened, but here it would never happen, it will never happen. So when changing situations, situation changes too. So it's very, very flexible. And this, if you talk about not taking circumstances into your thinking, right? When you don't think about changed circumstances, you will see it like a paradox. If we talk about liar, right? Liar. This is like, for example, the simplest example of paradox. What is changed when we discuss it? Like we say, liar. There are two cases of circumstances or context.
Lying or telling the truth.
First is he actually lied. He said, I lie. He actually lied. So we say, if we lie, if he lies, right? Then he says true. He's true. So what is lies here? We already we suggested already that he is right, and he is saying he lies. Really, this is actually the circumstance. This is the context already. We put this statement I lie. We put it under the certain circumstances. We added it. We just do not think about it usually, but we do that. So in this case, and the second case again. If he says true, if it's true that he lies, then he lies, right? So again, when we say if, we're using logic. If true, again, we already suggested that he is true. So we're adding something to the statement. It's not only statement alone. We put it into certain circumstances. And that's how it happens everywhere. With all the paradoxes, if you really think into it, it's maybe difficult in many ways, but it's true. So if you put in the certain circumstances, it would be no paradox actually, but it is a thing that actually depends upon the circumstances when you put it. So you're adding them by default, it's said, like by default. So something that we do not think right now, but if we really think, we will find out that we actually suggested already before that here he lies, here he says truth, and something else like this. The same thing in all and every paradox goes like this. Okay. Any questions on this? So context, just Mark noted for you that the context is very, very, very important. You cannot talk about like absolute things. At the moment when you talk about absolute things, you idealize them, and then starts paradoxes coming. Lots of paradoxes. Nothing is bad. Nothing bad is about paradox, but just for you to understand what is going on. And now about a little more about mathematics and axioms. So these axioms, laws, the same. They cannot be absolute true. They're true in our place, just again, in our part of the universe where we live. So they are very useful, but not universal. And but still, if we use this idealization, if we use this ideal that axioms are always true, this is not true, but some ideal, right? Like a tree, right? We were talking about one, right? Remember this tree. What is one tree? Idealization, everything like this. So axiom is sort of idealizations of that way. So if we talk about this, so we have some connections like axioms, between some connections, and then some theorems derived from this, right? We have certain thing which looks like stable. Because this is absolute true, then this is absolute true. This is theorem is proved, so it's absolute truth too. Everything is absolute truth everywhere, right? We have this system. It looks like very stable. It's like a bridge. In physics, it's called static. So it is very rigid. So it's not moving. We proved something from here, starting from the axioms, which are always true, and we create some system which is very rigid. It's like mechanical, called static, rigid, like system, like a bridge. Over what? Over ocean. Here is the ocean. Here is the ocean, and this ocean is full of paradoxes. It's all ocean of paradox.
So it's the axioms that are actually the problem.
No, they're not a problem. They're very useful. We use bridges, right? Bridges are very, very useful things. That's why our theorems and our theories are very useful things. We use them, and they are useful in our part of the universe. So bridge is okay when it connects one piece of land with another piece of land, right? And the piece of land are not that distant from each other. If they are too distant, it becomes lots of weird things becomes coming. So you remember, like in our small place, right? Euclidean geometry is okay. Going wider to our planetary system, solar system, it's already not okay. Going to the galaxy and the universe, it's totally off. So these static bridges do not work for the big and deep oceans. So what do we use to cross ocean if we want to cross this ocean? What do we use instead of bridges?
A submarine?
Yes, submarine may be good, yeah. but first came something simpler, right? But anyway, so some ships, right? So we use some some ships. And ships are very interesting things. If you look at them, they're at the same time partly rigid, right? They're inside rigid. But they belong to the waves. They jump on the waves, and so they look like the part of the ocean, right? So they are so-called dynamic. It's not static, it's dynamic. They are dynamic. And this dynamic, it allows us to cross the ocean. So it's like not a bridge, not the big rigid system, but a small system which actually is dropped into the ocean. It looks like it belongs to the ocean, but still it can save us and we can cross the big distances. So that's how works something else, which is not mathematics, but which is called language actually. Or another way, our mind. Our mind is that ship that's using language which allows us to cross the big oceans of understanding. And mathematics is just a part of it. It's coming. Parts of it can be refurbished, reformed to create a boats or whatever. So we would talk about something like this in the future from time to time. And now just I'm closing to finish. Okay, one term. Remember this symmetry transformation we talk about, like from darkness to light, right? From this to that, from nothing to something.
Hi, Nate. He's right here.
They are called. Just a term. They're called operators.
Operators.
Or that's symmetry transformation. I cannot write already. So symmetry transformation, actually it is called operator. So one is transformed into another. And this it can be written like this. Like this, another, like P. Like something, this one, like X, with the usage of P, is transformed to something else, like Y. Like this. Y is this. So P is called operator. Operator is applied to something which is variable or not variable, whatever. Like if you put here darkness, Okay, operator is a turning light off or on. So turning on light on darkness give you the light. And there may be inverse operator which goes back there and create like darkness from light. So just the word, it's just a term, operator. Operator. This is a general term for this. Okay, now just small talk about like some other paradoxes which very often appears, right? Like paradox of nothing. About liar and Barber we talk, right? Paradox of nothing. If you have absolute nothing, so it negates, denies itself. Remember? And if you denies nothing, there's something.
Yeah, that's what me and Vita said a long time ago about.
Yeah. So.
Can I tell you what something is?
Yeah.
Something is anything that you can say.
Yeah, actually it's anything because we don't know what is anything.
So something is nothing.
And nothing is
That's
something.
what me and Vita. That's what me and Vita. That's what playground, the car. No, not the car.
Remember, it's only when it's absolute nothing. Like darkness is absence of light, but if it's not absolute, right? It's still some light. So if it's absolute nothing, then it comes to anything. And if anything is absolute, you can find nothing here too. Absolute nothing, and it goes back here. So this is one paradox, right? Simple, for example. But then one many. This is closer to the standard mathematics, arithmetics and everything. Remember we were talking about ones, right? Equal one, and many of ones, right? Many of ones. So many always of ones. But each one is totally equal to each other one. Remember, in mathematics it's absolute things. So each one is absolutely the same one. So how can we be many of these absolute ones? There's a big question. Because there's still one. And if it's still one, the many becomes one. Yeah?
Vita,
Yes.
you said the more ones we get, the different each one can get.
Say it again?
You said in like 5 lectures ago
Uh-huh.
that for each one, after a long time, they get different. For example, one fir tree can turn into one mushroom. That's what you said.
What? No.
So it could be one fir tree. It's one. One mushroom. It's also one.
Yeah.
So ones can carry some different meanings behind them.
Yes, of course. We always, when we say one and many, we always say about one, not one mushroom and one tree, right? It's always one tree, and also not only one tree, but exactly particular idealized tree. Because trees are different, right? Remember? We cannot actually count different trees. Because we can call them trees, but we cannot actually count them. In the mathematics, because it's absolute things, one is always one. And in this case, because it's absolute one, not because there may be many ones, but not absolute. This is absolute one, like all abstract, idealized. That's why all the ones are the same. And if you take many of them, it doesn't make any difference because there's still only one. That's paradox again. Just think about it. It's very,
No, there's also -1. That's another one.
Right, if you add it, right? But okay, that's the only thing I want to say here, that there are lots of tricky questions here. If you really think about it, yes, we say, okay, that's 1 minus 1, right? It's already a paradox, because how can we write or even think about another one, because we already have one, if it's 1. 1 is not no others, just 1, and this is just 1, and they are the same. How can be the same if we even they were really the same? We cannot even think about them like as different. So it's already a paradox, right? And the same thing is like for 1. I actually told this. So this is paradox again, 1 and many, right? Like, yeah, to add this 1 this one can be actually set of many. So again, set of many, and still we talk about this as one. It's pretty interesting. Set of many, it's the same as many of ones, so it's the same thing. So they go back and forth again with the paradox. Guys, what is going on?
That's Sasha in the bathtub.
Okay. Okay. And now the third thing is I don't know. Do you know this? Just for the terms, but there is term. It's called discrete. Do you know this term?
Yeah.
Discrete and continuous.
Yep.
You know these terms? So there's not interrupted, right? No interruptions. Continuous.
I know those words.
And discrete is like parts, right? Okay.
I know. Yes, it doesn't know.
Okay. So here is discrete, right? And there are something between them, right? Discrete things, like particles, whatever. But when you look at this, picture, you see that something that is between them, right? It's actually a border. They border here, they border here, border here. All these discrete things, they actually are connected with the border, which actually make them continuous. They are connected. So even if you talk about discrete, just because the border has this paradoxical nature, it make everything discrete continuous, and back the same thing. Just for you to understand.
Like you don't know about it, right?
No, that's that's one meaning. Yes.
Like for example, many ones. It is a discrete thing, right? Many ones. One. They are separated from each other, right? But even if they separated, because they are just one, so this one and this one, if they are really the same one, are they separated? We pictured them as separated, but are they?
Yes, because there will be slight differences in them.
There are no any difference. They are the same. It is one. This is just one thing which we pictured twice. It's our picture is wrong, but so in actually two ones are the same. It's just one. So
I thought there would be two.
yeah, it would be two and one. Yeah, there's another paradox here. You can think about it, by the way. Okay, there's two other questions I want to ask you. The first is give example of paradox of your own, right?
Yeah.
Any. Actually, think about opposites as a clue. Think of opposites, and you will find out and discuss them, right? The second is examples of operators. So symmetry transformations in life and mathematics.
But isn't an operator is basically a function, right?
No.
I didn't
Function.
get the difference.
I would say that operator. Yes, function is an operator between one variable and another. Yes, it is true, but it's just one type of operator.
No, but if you assume that function can, if you assume that function can work on anything at all, then that's basically the operator.
No, this is basically operator. Function, it is about numbers. So argument to the result. So function is a little more, how to say, particular definition than operator.
Okay.
Operator is more general.
Okay.
Okay, and the third question is, okay, we have these things, symbols in mathematics that we use actually, like equal, right? Oh, no, what is this? Equal, then greater than, oh Jesus Christ, it's not, okay, greater than, less than, right? These symbols, which are else, like plus, minus, and what else? What do we have else? Yeah, like multiplication. Like, you know these symbols, right? We use them a lot. What are those? The question is, what are those?
What do you mean, what are those?
The operators, right?
In terms of, just think about it. You talk, please talk, discuss this, okay?
Okay,
Yes, that's true, but there may be a lot of questions, so just
Hold on,
Think
don't,
about it.
don't
No, I'm not removing it. I just showing this. Equal, greater than, less than, plus, minus, or anything you can find out in mathematics. What are those? What are those? Okay, guys. Now questions, if we have still. Any questions?
No, this was a good and interesting lecture. Thank you very much.
Okay, guys.
Thank you. This was fun.
Thank you. And